Hello friends, welcome to this YouTube channel. Today we are going to solve one numerical problem on three-phase medium length transmission line. By solving this problem, we shall learn how to determine generalized constants A, B, C and D of a three-phase medium length transmission line based on its nominal T equivalent circuit when transmission line parameters are given. We shall also learn how to compute percentage voltage regulation and efficiency of transmission for this line using these constants when load details are given. Using nominal T method and neglecting ligands, we have to determine the voltage regulation and the efficiency of transmission of a three-phase 50 Hz transmission line delivering a balanced load of 24 megavolt ampere 0.8 power factor lagging. Receiving end voltage is 66 kilovolts. Given resistance, inductance and capacitance per phase are 9.6 ohm, 0.097 Henry and 0.765 microfarad respectively. Let us first write down the given data. Load SL equals to 24 megavolt ampere, that is equal to 24 into 10 to the power 6 volt ampere. Line to line receiving end voltage VR line equals to 66 kilovolts, that is equal to 66,000 volts. For star connected system receiving end voltage per phase, VR equals to VR line divided by root 3, that is equal to 66,000 divided by root 3, that gives us 38,105 volts. Given load power factor cos phi L equals to 0.8 lagging. Let us now calculate power factor angle. Phi L equals to cos inverse 0.8, that is equal to 36.8699 degree. Expression for load SL equals to root 3 times VR line into IL. Therefore, load current IL equals to SL divided by root 3 times VR line. Using values we get 24 into 10 to the power 6 divided by root 3 into 66,000. That gives us 210 ampere. Load current may be written in polar form as IL equals to IL at an angle minus phi L, that is equal to 210 ampere at an angle minus 36.8699 degree. Here load current IL equals to receiving end current IR. Power delivered to the load PL equals to SL into cos phi L. Using values we get 24 into 0.8, that is equal to 19.2 megawatt. Given supply frequency F equals to 50 Hz, resistance per phase R equals to 9.6 ohm, inductance per phase L equals to 0.097 Henry and capacitance per phase C equals to 0.765 microfarad, that is equal to 0.765 into 10 to the power minus 6 farad. Let us now calculate inductive reactance per phase. XL equals to 2 pi F into L. Using values we get 2 pi into 50 into 0.097, that gives us 30.4734 ohm, and capacitive susceptance per phase DC equals to 2 pi F into C. Using values we get 2 pi into 50 into 0.765 into 10 to the power minus 6. That gives us 2.4 into 10 to the power minus 4 mho. Let us now calculate series impedance per phase of the transmission line. Z equals to R plus J times XL, that is equal to 9.6 plus J times 30.4734 ohm. This may be written in polar form as 31.95 ohm at an angle 72.514 degree. Shunt admittance per phase Y equals to J times BC, that is equal to 0 plus J times 2.4 into 10 to the power minus 4 mho. This may be written in polar form as 2.4 into 10 to the power minus 4 mho at an angle 90 degree. We have computed series impedance per phase of the transmission line Z equals to 31.95 ohm at an angle 72.514 degree, and shunt admittance per phase Y equals to 2.4 into 10 to the power minus 4 mho at an angle 90 degree. Let us now calculate Y into Z. Using values we get 2.4 into 10 to the power minus 4 at an angle 90 degree into 31.95 at an angle 72.514 degree. That gives us 0.007668 at an angle 162.514 degree. This may be written in Cartesian form as minus 0.0073 plus J times 0.0023. Now we shall calculate 1 plus 1/4 of Y into Z, that is equal to 0.9982 plus J times 0.000575. This may be written in polar form as 0.9982 at an angle 0.033 degree. For T equivalent circuit, A equals to D, that is equal to 1 plus half of Y into Z, that is equal to 0.99635 plus J times 0.00115. This may be written in polar form as 0.99635 at an angle 0.066 degree. B equals to Z into 1 plus 1/4 of Y into Z. Using values we get 31.95 at an angle 72.514 degree into 0.9982 at an angle 0.033 degree. That gives us 31.8925 ohm at an angle 72.547 degree. And C equals to Y, that is equal to 2.4 into 10 to the power minus 4 mho at an angle 90 degree. Taking receiving end voltage per phase as reference, we can write VR equals to 38,105 volts at an angle 0 degree. We have computed receiving end current IR equals to 210 ampere at an angle minus 36.8699 degree. For T equivalent circuit, we have computed A equals to D equals to 0.99635 at an angle 0.066 degree. B equals to 31.8925 ohm at an angle 72.547 degree, and C equals to 2.4 into 10 to the power minus 4 mho at an angle 90 degree. Expression for sending end voltage per phase Vs equals to A times VR plus B times IR. Using values we get 0.99635 at an angle 0.066 degree into 38,105 at an angle 0 degree plus 31.8925 at an angle 72.547 degree into 210 at an angle minus 36.8699 degree. That gives us 43,406.322 plus J times 3,949.783 volt. This may be written in polar form as 43,585.658 volt at an angle 5.2 degree. Sending end current per phase Is equals to C times VR plus D times IR. Using values we get 2.4 into 10 to the power minus 4 at an angle 90 degree into 38,105 at an angle 0 degree plus 0.99635 at an angle 0.066 degree into 210 at an angle minus 36.8699 degree. That gives us 167.5313 minus J times 116.202 ampere. This may be written in polar form as 203.88634 ampere at an angle minus 34.7457 degree. On no load, receiving end current IR equals to 0. Therefore, receiving end voltage per phase on no load VRO equals to Vs divided by A. Using values we get 43,585.658 at an angle 5.2 degree divided by 0.99635 at an angle 0.066 degree. That gives us 43,745.328 volt at an angle 5.134 degree. Let us now calculate voltage regulation, that is equal to VRO minus VR divided by VR. Using values we get 43,745.328 minus 38,105 divided by 38,105. That gives us 0.148 per unit or 14.8%. We have computed sending end voltage per phase Vs equals to Vs at an angle delta equals to 43,585.658 volt at an angle 5.2 degree, and sending end current per phase Is equals to Is at an angle minus phi 1 equals to 203.88634 ampere at an angle minus 34.7457 degree. For star connected system, sending end current per phase equals to sending end line current, and line to line sending end voltage Vs line equals to root 3 times Vs, that is equal to root 3 into 43,585.658, which is approximately equal to 75.5 into 10 to the power 3 volts or 75.5 kilovolt. Phase difference between Vs and Is, phi s equals to delta plus phi 1. Using values we get 5.2 degree plus 34.7457 degree. That gives us 39.9457 degree. Let us now calculate sending end power factor. Cos phi s equals to cos of 39.9457 degree. That is equal to 0.767 lagging. Now we shall compute sending end input power. PS equals to 3 times Vs into Is cos phi s. Using values we get 3 into 43,585.658 into 203.88634 into 0.767, which is approximately equal to 20.45 into 10 to the power 6 watts or 20.45 megawatt. Now we shall calculate efficiency of transmission. Eta T equals to PL divided by PS. We have computed power delivered to the load. PL equals to 19.2 megawatt. Therefore, eta T equals to 19.2 divided by 20.45. That gives us 0.9389 per unit or 93.89%. So today we have solved one numerical problem on three-phase medium length transmission line. By solving this problem, we have learned how to determine generalized constants A, B, C and D of a three-phase medium length transmission line based on its nominal T equivalent circuit when transmission line parameters are given. We have also learned how to compute percentage voltage regulation and efficiency of transmission for this line using these constants when load details are known. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends.